All right, everyone. Thank you so much for joining us for our talk. My name is Harsh. I got with me Rahul over here. I am a part of the product team at CoreWeave, and I'm here to share a little bit more about the lessons we've learned in terms of building high-performance computing cloud platform, some of the ways we've addressed customer issues over this time. Before I even kind of get started about like what CoreWeave is, what we've done, I wanted to get you a little bit of an understanding of how we came into existence, like why did we decide to build a purpose-built cloud for AI and machine learning workloads, and it essentially starts with the customer and the issues that they were facing. So throughout the history, like a lot of the workloads that the legacy cloud providers were trying to solve for were serialized workloads. The same cloud platform was being used to host a WordPress site, an e-commerce site, as well as maybe a data lake and do some analytics. It was not built for training large language models that required massive scale GPU infrastructure in the same facility connected through a fabric. So this is where CoreWeave came into play. We recognized that traditional legacy cloud providers were serving this market in an inefficient kind of manner, and we saw an opportunity for us to help customers out with this. And we essentially are looking at building the next generation of cloud computing, and the change happens across the stack. People ask us about, is it hardware, is it software, is it how you build your data centers? I tell them it is all of it. We start by looking at how our data centers are built, what kind of like hardware decisions do we make over here, and what kind of like software stack runs on top of that, so that customers that are building these models, that are serving these models, have a turnkey experience. Our customers are moving at the speed of light. You see the speed of models that's happening these days. Our customers do not have the time to set up their own infrastructure, to debug, to have an infrastructure operations management team, because at sometimes like it's just a team of 30 researchers that are looking at building the next foundational model. So we wanted to abstract all of that away from the customers and offer them an easy platform that's performant. And when I talk about architecture, hardware, and software, I wanted to get into the different layers a little bit more. So when we think about architecture, we are thinking of it from the data center design upwards. We work with our data center providers to design our data centers to our specific needs. We are not looking at a general data center where we will house a bunch of CPU nodes, of some GPU nodes, some storage, some network. Our data centers are purpose-built where we are looking at cooling, we are looking at power, we are looking at the network connectivity of these, because we realize that our customers require all of this to be at performant and to be at massive scale for them to do what they need to get done. So that's kind of like what we're looking at from an architecture level. As we move into hardware, this is where every single decision that we make, whether it is the compute that we're selecting, the networking that we're selecting, like for example, we use InfiniBand across the board. We use Spectrum-X when it comes to Ethernet. We have a partnership with VAST where we use them for their storage offerings, as well as we leverage NVIDIA's Bluefield DPUs for offloading some of the work that happens on the hypervisor layer to our DPUs. So we look at performance, we look at scale. We know that our customers are looking at like tens of thousands of GPUs in a single fabric, and that requires all of this to happen together for it to work. And then when it comes to the software layer, this is all, you've made all the right decisions to ensure you have a performant hardware. But at a software layer, there's a lot of investments that need to happen to ensure that not only is the performance translating to the customer, that there's also essentially a lot of uptime. Hardware inevitably fails. So we put in a lot of effort into automating the entire process so that if hardware is failing, if it is not performant enough, we are able to recognize that before even our customers do. And that goes everywhere from bringing up these nodes all the way through how our customers are interacting with our compute infrastructure. And this is where like Rahul will later get on into how we do like workload management. In the software layer, I want to talk to you about a couple of things in particular. The first one was our automated hardware validation and lifecycle platform. So CoreWeave was one of the first people to come up with the H100s in a massive GPU cluster. A lot of people ask us why. Like, this is one of the reasons why we are able to do it. We do not have an army of engineers that's out there that can kind of like install and debug things. So we automated everything. We have automated our entire bring up stack where we are able to put in the nodes into a cluster. And I'll show you what this looks like. But essentially, at every step of the wave, we have a full suite of tests that happens that's not just checking that if your connection is up, but it's also checking for HPC and InfiniBand performance. So we are continuously like testing for our customers that if anything happens, we recognize that before you do, so that you don't need to reach out to us and say that my cluster isn't performing, my training isn't happening at the performance levels that I need to. We can already isolate the issue if it is at an infrastructure level. And this is kind of an example of what the life cycle of a node looks like at CoreWeave. It goes in, things get plugged in. We first check and make sure that all the different components that are supposed to be there, all the memory is seated in, all the like storage that needs to be there, everything is present. So there's a check that happens for that. And then essentially it goes into a firmware app where we updated the latest custom firmware that we need. Post that, if something, like if all of it passes, it goes into a 24-hour burn-in period where we run a number of tests like Megatron, where like GPU burn, where we are not just testing that if this is a system that is up, that everything inside the system, all the connections that are there are performing at the level that they should, so that when you come in and you essentially come in and try to train your model, you are not testing that for the first time. So we are doing a lot of that for our customers. If everything works, it goes into production. If something goes wrong, it gets marked for triage. Somebody from our DCT team looks at it, fixes it, and then it goes back into the loop where we run all of these tests for the customers again. And these tests don't just happen when we're bringing up the nodes. We understand that like things can look fine one day. You change your model, or a firmware changes and things can look different the other day. So whenever a node is inactive, we have a suite of inactive tests that are running that are also continuously testing for performance from our customers. The second thing I want to talk to you a little bit about was DPUs. So CoreWeave is, like, we love Kubernetes. We offer a managed Kubernetes experience for everything, but we do not leverage hypervisors for that. We do not leverage VMs for that. Instead of hypervisors, we offload all of the processing over to the DPUs so that you get the full extent of compute capabilities from this. And this is not just for like managing Kubernetes experience, we're also exploring in our partnership with VAST, we're exploring how do we put VAST C nodes, which are the compute nodes, onto DPUs as well. This way, you get better security, you get better control, but it does not come at the cost of a performance delta and attacks on your compute. Going further, like I'm going to pass it off to Rahul, who's going to talk a little bit about like, all right, we've brought up the node, things are working. How can customers orchestrate the workload a little bit better, and what are some of the lessons learned there?
Hey everybody. We talked about kind of like the hardware layer and you know, monitoring our nodes itself and how we build you know, our data centers and make sure they're monitored. And once we go above that to the next layer to allow our customers to train on thousands of nodes, machine learning workloads that are distributed, you know, using distributed frameworks on thousands of nodes, which is not an easy task, especially with failure, you know, accounting for turnover, especially if the node has to go from a failed node, the workload has to go from a failed node to one that's actually functioning. We kind of want to demonstrate some of the tools that we have and we offer. Some of these are open source, some of these are proprietary, so we'll go through them. So one of the tools that we deploy is called Sunk, which is Slurm on Kubernetes. So it's a new concept. Usually Sunk Slurm is on an isolated cluster with, you know, a few nodes and people are running HPC workloads. We kind of took that concept of running Slurm as a workload scheduler and put it on Kubernetes. So now, along with the Slurm capabilities of scheduling, priority, being able to, allow for user access. It also allows for elasticity. So now nodes can automatically be provisioned on the Slurm cluster up and down. So if you don't want a node and you want to dynamically provision up and down to scale up to thousands of nodes, you can use our tool called Sunk, which allows for that. It's very intelligent, so it synchronizes state between Kubernetes and Slurm to ensure that both states are managed internally. So we build we build our own controllers to be able to do that. We want to open source it in the near future. It's developed with input from SCEDMD, who were the original innovators of Slurm. And it allows for large-scale training. So we've trained the new MLPerf 3.0 benchmark on thousands of nodes using Sunk. And it's very useful for us to be able to deploy large-scale workloads. Another tool that we offer, so we talked about training. So one of the tools we offer is Sunk. You can even go onto Kubernetes and deploy your own operators or deploy your own training workloads with distributed frameworks like PyTorch. And now when we move on to inference, the other framework that we offer is called Tensorizer. It's open source. You can go find it on GitHub. And the key advantage of Tensorizer is it's the fastest state-of-the-art framework to allow for model loading and model checkpointing in the industry right now, compared to Hugging Face or Safe Tensors, which is supposed to be state of the art. And how we do this is we take your model file, your large model file, and we serialize very fast into a single binary file with metadata up front. So all the metadata and the headers are stored at the front, at the initial kind of header of the file, and then sequentially all the tensors are loaded right after. So when we're deserializing and loading onto a GPU, we read the metadata, we know exactly where to put these tensors in the GPU, and we don't use RAM or we don't use CPU memory. So if you're loading a Hugging Face model, for example, you would have to you have to put the model onto CPU, which if it's a model that requires a lot of RAM, you need directly proportional CPU RAM, and then you offload that model onto the GPU. We don't allow for that. We actually use one buffer, which is the size of the largest tensor, and we automatically offload the model directly onto the GPU, about 5 to 10x faster than what Safe Tensors does. So this library is available online for you guys to check out and use, and it makes model loading, especially for inference, in any format, in FP8, FP16, very, very fast. So we've seen 2 to 3x faster model loads on network volumes, and when you want to load from object storage, which is kind of the common use case, we've seen 3 to 5x faster model loads. And this is very useful, especially if you're running an inference application that, like a chatbot, and you don't want downtime for users, where users are interacting with your chatbot and then they have to wait a minute to be able to get another response when you're auto-scaling because of large bursts in traffic. We kind of obfuscate and allow for for you to be able to scale to millions of users very fast compared to generalized cloud. So how it looks is a user comes in, hits an HTTP or HTTPS endpoint, your API basically. If there's not enough pods to serve the request, the autoscaler triggers a new pod to come up. And then Tensorizer is responsible for loading the model from object storage or NFS and serving the model. We've seen in total, for the whole end-to-end cycle of loading the model, running it, and processing requests, 8 to 10x faster response times compared to generalized cloud that we observed based on our benchmarks. So again, just to emphasize, to summarize, very little CPU usage. So you're basically not paying for any more RAM while loading models onto the GPU, and extremely fast model loading with support for streaming. So the network bandwidth that you're using is very minimal. And the last tool that I want to kind of present to you is our partnership with Weights and Biases. We recently came out with this product in integration with Weights and Biases, and it's called Launch. So you've heard of Launch. You've probably seen it in the keynote running the NIM, and we've integrated it onto CoreWeave. And so what it allows you to do is to take your workload, if you're running it on a laptop, anywhere that you're running it in a compute cluster, it may be on premises. It allows you to take that workload and and deploy it on different hardware when you actually want to scale and start experimenting with it, instead of kind of running it on your local workstation. And that's the idea behind it. So you have a one-click push. So you take your workload that you're basically prototyping with sample data. You want to be able to push to production with maybe a terabyte of data. You just need to click on one button, add some configuration, and you should be able to deploy it in production or on your Kubernetes cluster. You can account for different resources that you want to deploy it on, different hardware, different configuration, and you get a lot of visibility, which is the whole reason behind weights and biases being adapted by the entire ML industry. You can also rerun these jobs. So once you run your jobs, once you run your code, they're basically jobs that are artifacts stored in weights and biases. And you can tweak your hyperparameters, do sweeps with weights and biases to be able to optimize for the best hyperparameters and the best metrics that you account for in your machine learning model. And you can rapidly iterate to be able to monitor, visualize, and understand which is your best performing iteration of your model to be able to deploy it for your inference use case in production. As you can see here, we're basically changing the learning rate, maybe some other parameters, and basically deploying it onto your workload manager. On CoreWeave, it's as simple as clicking one button to be able to run a 1DB launch agent. So we have it on our catalog. You literally go click on it and you say deploy, and you have a 1DB agent running that's able to run your machine learning workloads on CoreWeave infrastructure and scale up to thousands of GPUs if you'd require, along with optimized distributed training patterns. So our whole proprietary stack on CoreWeave offers for optimized networking, optimized distributed training. So we configure the images and all the libraries that come with distributed training to be able to run as fast as you can and as reliably as you can on CoreWeave. And that's why we have large-scale machine learning workloads currently running as we speak. Recently, we did a blog post with weights and biases, and we ran Mixtral, so to give you kind of like a real production use case of how this works. As you can see, in the demo, we change a bunch of configuration parameters, and you can monitor each of your runs. And we ran one of those that actually succeeded. All these jobs are versioned. They're stored as artifacts. So if you have any problem reproducing your experiment, you can just go back, check your artifacts, check the version that you ran, check the metrics, and ensure that you get what you want out of your machine learning workloads. And finally, just to kind of conclude how this all fits together, once you run your machine learning workload, you can monitor your impact of the hyperparameters, different charts to monitor train, eval loss, and everything that's going on in your experiment to be able to understand it more intuitively. And the best part is that once you run these launch agents, you can run it across different environments. So if you have an environment that runs PyTorch and another environment that runs TensorFlow, you're able to deploy the same workload on these different environments with weights and biases launch. And you can also set priority based on how you want these workloads to schedule and when you want them to schedule. Preemption works as well based on priority. And everything is configurable right in the UI. The amount of GPUs you want, the runtime you want, what queue you want to run it on, which infrastructure you want to run it on. So it's configurable across all your environments, and you can monitor and control your workloads. For more information, please scan. But yeah, happy to answer any questions about CoreWeave. Thank you.